Hello! In this video, we're going to do another one-dimensional kinematics scenario. In this case, we're going to have a ball thrown up into the air. Okay, so I'm going to write down our scenario. So a ball is thrown directly, no, I'm going to say straight up, just straight up, straight up at 4 meters per second. So we're gonna have two parts. So we're gonna have part A comes before part B. How far does the ball travel upward before hitting, I'm gonna say before reaching max height? My handwriting is atrocious, I'm so sorry. And then part B is how long was the, say for how long? So, how many seconds was the ball traveling? Okay. So, the first thing we're going to do in this situation is draw a picture. So if our ball is right here, it's traveling upward at 3 meters per second. Okay, and then we have our coordinate system right here, like this. This is all we know. We're told in part A, we're asked to find how far does it travel before reaching max height. So there's one thing to note. Whenever something, at least in physics 1, whenever something is thrown upward or launched upward in some velocity, at the max height, velocity is 0, because that means your object is traveling upward. I'm actually going to use I think it's like this, yeah. Ooh. The motion diagram thing. Okay, so it does this. So at the bottom, it's moving at some meters per second, and it slows down as it reaches the top. And at that top, the reason why it's no longer going upward is because its velocity is 0. And then it will start to fall back down and speed up as it falls. Okay? This method, this how do you phrase it? This kind of process also applies to two-dimensional kinematics and some other stuff down the road. So just know that your object, in our case the ball, at max height of its vertical direction, velocity is 0. Velocity in the y direction is 0. And since we're only dealing in the y direction right now, that means that the velocity is 0. And then another thing is that since we're dealing with a object being launched upward into the air, we already know our acceleration. And our acceleration is gravity. Because gravity is the only thing, we're assuming that there is no such thing as like air resistance and all that. Gravity is the only thing that is keeping this ball from going off into space. Gravity is the thing that's pulling this object back down to Earth. But gravity isn't strong enough to make sure it doesn't leave the ground in the first place, which is why we can jump up, like we as people, we can jump, but we always fall back down to the ground. It's because we can, I guess, negate gravity for a second or two before its acceleration due to gravity pulls us back down to Earth. And that's what this ball is doing. Okay? And how this ball like got launched or whatever, that doesn't matter right now. The only thing we care about is that its initial velocity is 3 meters per second. Its final velocity at its max height is 0 meters per second, and its acceleration, because it is in the vertical direction, is gravity, which is 9.81. Okay. And there are two ways you can figure out which direction this gravity is going to go. So gravity is, so this is, let's use green to denote the ground. If this is I said green, fine. We'll use green to denote the ground. So if this is the ground, gravity is always going to pull downward, right? And according to our axis right here, positive y is upward, which makes gravity negative because it's going down. That is one way to think about it, and that's completely right. Another way to think about it, and I touched on this in my free fall video, another way to think about it, and this is the way I tend to think about it, because this is easier to think about later on. When you do 2D kinematics and stuff, at least in my experience, it's always kind of resonated with the people that I tutor more. And that is your acceleration is going to be positive if it's working with your velocity, your initial velocity, and it's going to be negative if it's working against your initial velocity. So if gravity is going down, if acceleration due to gravity is going down, we'll say, and our velocity is going up because our ball is being launched upward, that would make acceleration negative 9.81 meters per second because it's working against velocity. That's meters per second squared. Okay. Either one of those ways to kind of puzzle out which direction or which sign A has, they're both fine. Just make sure you're consistent throughout your problem. Okay. So, we want to know how far the ball travels upward before reaching max height. I did not write down the kinematic equations in this scenario. If you don't know what they are, I know some professors and the internet and everything, they have subtly different ways of writing them, but there are 3 equations. And because there are different ways to write them, I'm just going to write down the ones that I'm used to using as the need arises, because I don't want to, give you a formula bank and it not match up to the ones that you're supposed to use in your own classes, or, the ones that you've used in the past if you're just refreshing yourself. Okay, so part A is distance. So how far does the ball go? That is distance, which means we're going to want to use the kinematic equation that relates velocities and acceleration and distance all together. And that is VF squared equals VI squared plus 2A delta, I'll say Y because it's in the Y direction. Okay? So our final velocity is 0 because at max height, velocity is 0. And our initial velocity is 3 meters per second. That's not a second, that's a 2. Second, and that is squared, plus 2 times negative 9.81 because gravity is working against the velocity, so it's negative. And then this is multiplied by y. And that delta y is the number we're looking for. So if I were to plug this stuff into my calculator, I would get 9 meters squared per second squared equals, wow, 9.81 times 2, 19.62 meters per second squared, and this is multiplied by y. So if we divide over, because I took this, moved it to the other side, okay? So then if we divide 9 by 19.62, we get 0.4587 meters. That's it. So our ball travels a little less than half a meter up into the air before stopping, before reaching max height. Now, this does not tell us how far the ball travels, like in its entire path of going up and then back down. This is the instant, so like if I were to draw this over here, so we have the ball going up and reaching max height, and then we have the ball going down back to its initial spot. Now, these two would be superimposed on each other, more like this, because the ball isn't moving horizontally, it's staying strictly straight up and down. But for simplicity's sake, I'm going to leave it like that. So what we have just found was the distance the ball went from here to here. We don't know how far the distance, like how far the ball goes like this on its way down. A little shortcut is that we can kind of assume that it's the same distance. So whenever your object or whatever, as long as it begins and ends on the same, like in the same spot or the same height. Okay, so right now, since we're dealing with 1D, since it would begin and fall at the same spot. So if you throw it up into the air, like if you have a ball and you throw something up into the air and you catch it at the exact same height above the ground as where you threw it from. So like, if this is the ground and you're right here and you throw the ball from your hand like this and you catch it right there, right where you threw it, instead of it hitting, like maybe it hits the ground. If it hits the ground, this thing that I'm about to tell you about doesn't apply. But if you catch it, or if this ball lands exactly where it was thrown, like the exact same height from which it was thrown from, all of this right here, so everything that happens from the first half, so from when it's launched to when it reaches max height, is symmetrical to max height back to where it started from. So it takes the same amount of time for the ball to fall as it does for the ball to rise, and it has the same velocity. So the velocity at which it leaves your hand is the same velocity at which it hits your hand, and the velocity at the top, that is at its max height, is still 0, and the acceleration is still 9.81. It's just on the way up, it's a negative, and on the way down, it's a positive, because on the way up, it's fighting against that, what's it called? It's fighting against the velocity, and on the way down, it's helping velocity, because it's pulling the object back down to Earth, which is the direction it's going anyway. And then another thing that's the same is the height at which the ball goes up, and the height at which the ball falls down. Now that doesn't work, that kind of like way of thinking doesn't work if you throw it into the air, but then maybe you let it hit the ground. Then it doesn't work, because then you have this additional distance that it travels. So it's no longer symmetrical. But that was a bit of a tangent, and that's kind of keep that in the back of your mind, especially when you do 2D kinematic stuff. It'll be very handy. Part A just asks us to find the distance it travels before it reaches max height. So that's from, I guess we'll use this color. So that's from here to here. That's it, which is what we found right there. Half a meter, roughly. That's it. That's part A done. Okay, and then part B is how many seconds was the ball traveling? So in this situation, where you can either use, let me write them down. We can either use this one, or we can use this one. Okay, they will both technically work, okay? We are looking for this variable. I'm gonna go ahead and tell you, always use the easier equation. This second one right here, it will be a nightmare to solve for time with that formula, because time is in there twice, so we would have to use a quadratic equation and do some square rooting and all of that, and it's a mess, so we're not even going to try it. We're just going to stick with the easier one. And that is, our final velocity is 0, and our initial velocity is 3 meters per second. Our acceleration is negative 9.81, and our time is delta t. So now we're going to move the 3 to the other side and divide by 9.81. So we get negative 3 equals negative 9.81 t. And then delta t equals negative 3 divided by 9.81. T equals 0.305 seconds. And the reason why it's seconds is because if we compare units here, I'm going to use this guy. So 3 has a meters per second. That's not a second, that's a 2. And the 9.81 has the unit meters per second squared. So this is divided by meters per second squared. Okay? And whenever you're dividing two fractions, you do the keep it, change it, flip it mentality thing. It's been a while since I've used that. Last time I think I've actually used that is like in grade school, because normally I can just plug in fractions into my calculator, but this is how we're checking units. So we then get meters second squared over meters second. And our meters, I'm going to use a brighter color. Our meters cancel, and one of our seconds cancel. So we are left with seconds, which is how we know that our math is correct. So this is our final answer. And these two things, where's my mouse right here? Okay, so these two things that I have boxed in, the y is the distance from launch to the max height, and the time is the time it takes for the ball to go from launch to max height. Okay? The actual time it takes for the ball to complete its path and go back to its original spot is t times 2, because it starts and stops in the same spot. If we go back to our guy, it starts and stops in his hand. Okay? And because it starts and stops in his hand, the time it takes for this whole thing to happen is just 305 times 2, so 61 seconds. Okay. I have lost the ability to write seconds. That's how the time it takes for the whole scenario to occur. Okay? Same with velocity. Or not velocity, wow, same with distance. So if it takes 0.46 meters to go from the guy's hand to the max height, it would then take, oops, I used the wrong button. It would travel 0.94 meters to go from the hand to max height back to the hand. assuming the hand doesn't move. Okay? I hope that made a little bit of sense to you. I know this is when kinematics starts to get a little fun, I guess I'll say. It gets a little more complicated now. I plan on having videos that kind of show all, like, the whole range of how complex kinematics are going to get, at least for Physics 1. This guy, if you can do this, you are pretty well prepared to start two-dimensional kinematics. If this is a bit confusing, I would recommend spending more time on this style of 1D kinematics, where your ball has two parts to its movement. So it has the part from the throwing to the max height, that's part 1. And then it has part 2 from max height back to the ground. I would focus on that kind of kinematics before you launch into 2D. And I will have another video on that. It'll be kind of a continuation of the one-dimensional car kinematic video that I did. But I do believe that is about everything for this topic. If you have any other topics you want me to cover, feel free to leave a comment. And I hope this helped you some.